I hope you had a good 3-day weekend. My phone died, so now I have an old phone that doesn't work as well. So I guess I get to go hang out at the Apple store later. I just did this cool thing where I was using it, and then the Apple logo came up, and then it just turned off forever. So I don't remember getting it wet or anything, but here we are. So that's how my weekend went. It did go to the beach with me, so maybe it got sand in it or something. And we're going to start with finishing up Chapter 2. So I'll have the videos posted for Chapter 2 after this class, but if you're here, you're already here, okay? So let's talk about one-dimensional motion with constant acceleration. And I'm going to do just sort of, we don't do a lot of derivations, but this one is important, so I'm going to start by making a few assumptions, okay? So remember, we talked about the definition of velocity and acceleration, right? So what's the definition of velocity? Yeah, it's going to be, let's say, ds, right, dt, and these are vectors, all right? And then for acceleration, we have dv, like dt, so the derivative of velocity with respect to time. It's a vector, it's a derivative, that's the formal definition, okay?
Can you make that a little bigger? I'm so sorry, I don't have my glasses, and I can't see. What is that above the V?
It's just a vector symbol.
Above the V?
Above the V, yeah. I don't know if I can make it actually bigger.
It's fine.
I can zoom in. I'll try to write bigger. There we go. How's that? Better? Okay. So the other thing we've learned about is average velocity, which you can write as delta S, delta T, right? So that means there's an average acceleration that's delta V, delta T, okay? So what's the difference between the derivative and the delta? We talked about the various D's of calculus, right? The D's of math. Delta is a capital D, so that means it's a big chunk of stuff, right? So when are these two things the same? When is average velocity equal to instantaneous velocity? Yeah, when you have a constant speed, right? So as long as you have a constant speed, which we call uniform motion, right, or constant motion, then you know that these are going to be the same. Okay? Same with acceleration. If you have a constant acceleration, then these things are equal, but only if you have a constant acceleration, okay? Now, that means if you have a constant acceleration, you can write acceleration is equal to delta V over delta T. Sorry, I keep changing the way I write V's, but you get the idea. So even though this isn't the definition, right, this is the definition. This is true for, we'll call this true for constant acceleration. And nothing else, okay? Otherwise, it's just an average acceleration. Okay, so starting from that, you can rewrite this so that we have, let's just rearrange it. I'm going to drop the vector symbols just for ease of use. But if we rewrite this as delta V over delta T, we can pull this over and have delta V is equal to a delta T, okay? Which is the same thing as, remember, delta V is V final minus V initial, so that's going to be equal to a delta T. So that means you can write V final is equal to a delta T plus V initial, okay? This is actually our first kinematics equation. So we've been talking about kinematics. This is our first constant acceleration equation, and it's the velocity equation. You'll also see it written sort of like V final is equal to V initial plus a delta T, okay? Those are the same thing. And the reason we write it like this, what equation does it look like? Yeah, it's like y equals mx plus b. We know it's linear, okay? All right, one step further, what if we want to figure out position? How do we get position from this? We have velocity, right? We have an equation for velocity, and it's with respect to time. How do we get position? integrate, right? So we can rewrite, so this is a constant, right? We've talked about initial conditions, so this one's a constant, but this one isn't. It's a function of time, okay? So if we want to integrate, we have to do this. We say, okay, velocity is the position, and I'm going to use x in this case just because I think s is a little bit confusing. So we'll call this dx dt, all right? That's our definition of velocity, and that's going to be equal to v naught plus a, we're just going to call this t just for simplicity. We're skipping some like math details, but the physics details are all there. Okay, so what we do is we say dx is equal to v, oops, that's ugly, v naught, which is a constant, plus a, which is also a constant, t, and then we bring over our dt. Now this is less kosher in math, but it's totally fine in physics, so we're going to go ahead and do it. That means we're going to integrate both sides, okay, because now we have a d something on each side. So this is going to give us x, which is kind of an x plus c, right? But we can also say we're going from initial to final. So you could say this is x final minus x initial, okay, which is equal to v naught. What would we do here? We're integrating with respect to t. This is a constant, so it should be v naught times what? T, yes. And then this should be plus, this is a t, so you do 1/2 t squared. So 1/2 a t squared, okay? So that we end up with an equation that looks like x final is equal to x initial plus v naught t plus 1/2 a t squared. Now, if you've taken physics before in high school, does this equation look familiar? Yeah, these equations are the kinematics equations that they just make you memorize, but they're actually really easy to derive. They just come from the assumption that acceleration is constant, right? We just started from this assumption that acceleration is constant, and then we were able to get this by just solving it to look like the equation of a line, which isn't even actually changing the equation at all. So this actually still says acceleration is constant. And then to get position, we just took an integral. Now there's a third equation that doesn't have time in it. Guess how we get that one? You actually don't have to do that. You can just solve this one for t and plug it into the other one, and then you just have that third equation that gets rid of time. But so I'm not going to go through the derivation of that. That's just algebra. But what I think is the really important takeaway from these is that you get these equations from knowing that acceleration is constant. So should you ever use these equations if you have a non-constant acceleration? No. Okay, so hopefully that helps us to remember, but also we were able to use the math we already know. There's no complicated math here, and the assumptions that we've already made to get these equations without having to memorize them. Okay, and not a lot of you are trying to become physicists, but in physics, all equations that you use, you have to know where they come from, and that means you have to start from just the base assumptions. We call that deriving things from first principles, which is just by knowing the facts about the stuff you're dealing with, you can come up with an equation to deal with it. Okay, it's a fun skill. Oh, I have somebody in the chat. Oh, they just said hello. Okay, okay. So we're gonna go back to the slides. Okay, so we're talking about one-dimensional motion, but now with constant acceleration. And remember, we talked about other constants. I'm going to turn this off. So remember, if we have constant velocity, what does that tell us about our position? What shape is our position graph? Is it flat? Is it slanty? Is it curvy? Linear, right? So that means that's, what about our acceleration? What's our acceleration if our velocity is constant? Zero, because we don't have any changes in velocity, therefore we have no acceleration, okay? What about if we have constant acceleration? What should our velocity line look like? Should be linear, right? Then what about our position graph? I like these this dance that we're doing. Yeah, it should be parabolic, right? Because we're going from linear, which should be t, like we just did in this derivation, right? So it should be linear in time. And then when you take an integral of that, it should give you a power of 2. Okay, so it's a parabola, which means it's like a quadratic equation type situation, but it's curvy, okay? But it's a special kind of curvy. It's a power of 2, not 3. It's not an exponential. It's not a sine. It comes from the fact that if it's something's linear and you take an integral of it, it's going to give you something squared, okay? Cool. So remember, constant acceleration is not always constant, so you have to pay attention to that. But when it is, you can derive these equations that we just went through. And this is just the one that comes from combining the other two. And these are our equations of motion, okay? They describe motion. So if you know something about the speed and the position and the time, you can figure out other variables, okay? So this is where you end up doing a lot of algebra in this class, because we generally know something like this and we want to find this. So and sometimes we have to use more than one equation. We'll get into the details of how we use these equations, but we're going to use them a lot. Okay, all right. If you haven't grabbed a clicker, go grab a clicker. Oh. Okay, we are all over the place. Please discuss, we'll vote again. So we're thinking E mostly, which is good because that's the answer. But why is it E? So first off, can acceleration be negative?
Yes.
Yes, which one's negative?
A.
A. So here we have a negative acceleration, we have a positive acceleration, and what do we have here? 0 acceleration. So it should go positive, 0, negative, and that answer would be E. Okay? So be careful of sign. Remember, negative slopes mean something different than positive slopes, so that's what we're representing here. All right. That's the arrow. Cool. Okay. So, we're going to go through this together. It's just going to take up a lot of space for me. But we're going to try applying these equations. This is the first real physics equation, real physics problem we've encountered in this lecture section of class. And so it's just like a word problem on steroids, okay? We'll go through it together, but basically starting from rest, we have a rocket sled. Does everybody know what a rocket sled is? No? It's like when you attach a jet engine to a terrestrial moving object. So it's just like jet propulsion on like a cart. They use these to do like G-force experiments on people and whenever we started sending people into space. So it turns out, I think 5 Gs is about how much you can take before bad things start happening to you. So fun fact. So if you're attached to a rocket, that's what you should be thinking about. So it accelerates at 15 meters per second squared, which is slightly insane, for 5 seconds, coasts for 3 seconds, and then deploys a braking parachute and decelerates at 3 meters per second squared until coming to a halt. So we want to know what's the maximum velocity of the rocket sled, and then we also know what the total distance traveled is. Okay? So I'm going to do this with you guys. And you can just follow along because I just want to show you sort of how we set up these problems. All right. So I hope you can all see. So we start from rest. So first off, let's look at the problem itself. Okay. So what information do we have that's useful?
I'm thinking accelerates. I'm not sure though, but accelerates.
Accelerates matters. What does start from rest mean?
Initial point.
Yeah, starting from rest means that we can assume that our initial velocity, right? Velocity initial is equal to 0. Okay, 0 meters per second. And then it accelerates for 50 meters per second squared for 5 seconds. Okay, so we could say for time interval 1, let's call this phase 1 because rockets, So we'll say phase 1. Ugh, hang on. I'm gonna start over. Okay, so phase 1. We have an initial velocity of 0 meters per second. We have an acceleration. We'll call this acceleration 1 of 50 meters per second squared. And we have a time interval delta t of 5.0 seconds. Okay, and so we got these from, this one is from here, right? Then we have our acceleration. Accelerates at 50 meters per second squared. That's our acceleration. And then we have our time. I guess I'll make time purple. Time will be 5 seconds. Okay, so that's where we're getting those things. So that's our first phase. Then what happens? Okay, we'll call that phase 2. Okay, so in phase 2, we coast for 3 seconds. So what's our initial velocity now for this part? We'll probably have to figure it out, right? Do we know what it is? No, we don't know what our initial, so we'll say V1, right? So we'll call this, there's going to be a V final, and that will be the same as the V1 here. So we'll call V final V1. Okay, we don't know what that is, okay, because we have to figure it out from this first part. What's our acceleration in this period?
0.
Yeah, our acceleration is 0 because it's coasting, right? So that means it's not accelerating. And then what's the time interval? Well, the time interval is going to be, let's call this time interval 2, is going to be 3 seconds, okay? But the other thing I want you to realize is this goes from time equals, so t0 is equal to 0 to t1, which is equal to 5, right? And then this one goes from time 1 equal to 5 seconds to time 2, which is equal to what? 8 seconds, right? Because we have to add those two together, okay? So we have this coast for 3 seconds. So 3 seconds goes here. Here's the coasting part. And then we have one more phase, right? So in phase 3, we deploy a braking parachute. So we don't know what our initial velocity is here either. But we know our acceleration 3 is going to be 3 meters per second squared. Is it positive or negative?
Negative.
Yeah, so that's going to be negative 3.0 meters per second squared. But we know our V3, our final velocity, is 0 meters per second. Okay? So essentially, if we draw this out, we have this sled. I'm just going to draw it like a stupid car. Okay? So we want the total distance. We'll call this x. And so this sled starts at x equals 0, and this is at time equals 0 seconds, and then it accelerates from here to here. So let me see. Yeah. Right? In fact, the bulk of the motion is probably going to be here and here. So we'll have, this is phase 1, phase 1, right? Phase 2 and phase 3. This will be the distance each of them goes because that's the first thing we're looking for. Well, first we want the maximum velocity. When is the maximum velocity going to happen?
Phase 1.
At the end of phase 1, right? So our maximum velocity has to be here. Why does it have to be here? Yeah, because our acceleration stops after this, so the velocity can't get bigger, and then later we have a negative acceleration, so the velocity is only going to get smaller. So that means we're going to try to figure out V max here, okay? But we also need to figure out distance, so we're thinking of both of those things. So this means this will be, we'll call this x0 equals 0 meters. This will be x1, which we don't know, and this will be x2. So we'll go accelerate, coast, and then finally there'll be some x3, which is our final velocity. And this is the other thing, or sorry, final velocity, final position. And this is the other thing we want to find. Okay, so total distance traveled, that's over there. And the maximum velocity, those are the things we want to come up with. Okay? I don't have a ton of space here, but we'll try to do it. So we know all of our knowns. We know what our unknowns are. We have a picture. So the picture, we might want to label some of the things. We might want to say, for instance, that here we have an acceleration of 50 meters per second squared. Here we have a deceleration of 3 meters per second squared. These are not drawn to scale. And here acceleration is equal to 0. Okay? Then we'll have to go in and label the other things. We also maybe want to write in that velocity here is 0. Anything else we want to include? Times, maybe? So this would be t equals 5 seconds. This is t equals 8 seconds. And then we don't know what t equals here. Okay? Cool. And just, this thing's moving this way. What equations might we need to get started on this? Yeah, just to start out with, to do A, we want to know the maximum velocity. So we could just use the standard velocity equation, which is V final is equal to V initial plus A delta t, right? This is the equation we just came up with. It's just the velocity equation for a constant acceleration. So we can change the labels around. So we could say V1 is equal to V initial plus A1 delta T1, right? So we can plug in our values. We know that this is 0 because we have that over here. We know that acceleration is 50 meters per second squared, and we know that our time is 5 seconds, okay? So when we multiply these together, that means we are at 250 meters per second, and this should be our V1, but also our V max, okay? And that should be in the forward, the positive x direction if you want to write it as a vector. So we'd call that x hat. So that's our first, oh, that's not great. My vector is sticking out, but you get the idea. Okay, so that's our first answer for part A. So if we want to say, here's part A, here's the answer to part A. Okay, now I'm going to make this smaller. Okay, general idea is good. All right, so that's part A. What about part B? Part B is going to be a little bit more complicated, right? Yeah, we need position, but we need position 3 times, okay? So we'll start with part B. We need the position equation. We have 2 position equations, though. Yes?
Didn't you use the time that it took you with the acceleration to find the position?
You can, yes.
You're accelerating for a certain amount of time.
Yeah, you can do, for the first part, that's a good idea. Okay, so for the first part, we want to use, there's a couple different, we can actually use either equation for a lot of these parts, but let's start with x final is equal to x initial plus v initial t, oops, delta t plus 1/2 a delta t squared. Okay, can you guys see that? Is it super tiny? So we can say this is x, we want to find x1 is equal to x initial, let me make these a little smaller, plus v initial delta t plus 1/2 a1 delta t squared. So this is just for the first phase. This is just to find this position, okay? So we know that this is simple because this is 0, right? Because we know that this is 0. What about velocity? Also 0, right? So when we actually write this out, oops, x1 should be equal to 1/2 a, which is 50 meters per second squared, times 5 seconds squared. So our first position, our x1, should be 625 meters, okay? So 625 meters. So that means right here, x1 is 625 meters, all right, in the first phase. Okay, what's next? This is just phase 1. So now we want to do phase 2. So we start at 625 now. So we need to figure out what happens between 5 and 8 seconds. Okay, do we have acceleration? What is it? 0. Okay, so we have 0 acceleration. We know our initial velocity for this period. So this one's actually pretty simple. It's a constant velocity. So we know that constant velocity, delta v, right, is equal to delta x over delta t. Because it's a constant velocity, we can write it that way. It's not a derivative, okay? So we can solve for this. So that means our delta x here, so delta x2 is going to be delta v delta t2, okay? Our change in velocity isn't anything. Oh, sorry, delta x. Yeah, so this is just velocity. We don't need change in velocity. Sorry, should not have written it like that. So v delta t. So our velocity is 250 meters per second, and the time is 3 seconds. So that gives us what? 750. So that's the change, though. So that's the change in 3 seconds. What is our actual distance now? Yeah, so our x2 is going to be delta x2 plus x1, which is 750 plus 625, which is 1375. Okay, so that means right here, we are at 1375. All right, so just to follow along, we go from here over to here, and previously we went from 625 over to here. Okay, what do we still need to do? There's one more phase, right? So phase 3. So now we know we're decelerating, but we're still moving forward, right? Because we have a velocity over here in this direction. We start at 250, and that we have an acceleration going in the negative direction. So how do we write that? Well, we're going to need to do one of two things. Do we have time in this case? So should we use the other equation that we haven't used yet? Okay, so our final equation is v final squared is equal to v initial squared plus 2a delta x. Okay, let me move this over so I can actually have some space. What is our final velocity at the end of phase 3? Yeah, that's going to be 0 because we know it comes to a stop, right? So we know this goes to 0. Our initial velocity? We do, right? It's been coasting. Has it changed velocity? Still at 250. So this will be 250. And then our acceleration is -3, and we're looking for delta x. So we're going to solve this for delta x. Remember that we know acceleration is going to be negative, so we can change this to a negative value. And just don't forget to, don't negative twice, okay? Since we know it's negative, I'm just doing it to make the algebra easier. Now you just plug in 3, because you've already plugged in a negative. So that means we have v initial squared is equal to 2a delta x. We want to solve for delta x, so that's v initial squared over 2a. Now why am I solving for x first? Because it's easier to do algebra with variables than with numbers, okay? So I'm solving for the variable that I want, and then I plug in the numbers last. You don't have to do this, but it tends to be cleaner. And the extra added thing is now you see the relationship between the variables here instead of just a bunch of numbers, okay? So we know that if it goes faster, it's going to go farther. So that means we have 250 meters per second. We're going to square that, and we're going to divide it by 2 times 3 meters per second squared. The delta x here is going to be, oh cool, I didn't write that one down. Phase 3. 10,416. 10,416. Oof. Okay, so it's equal to 10,420 meters. Okay, so that plus, are you sure?
So it's 10,416.6 would be
Let me see. Okay, I'm just gonna, not that I don't trust you, but I slightly don't trust you. I'm just gonna do it on my calculator. Oh, I don't have a calculator. Cool. This phone sucks. Oh no, there it is. Okay, so 250 squared. Jesus. Divided by 6. Oh yeah, okay, you nailed it. All right, so that plus 1325. There's 1375, shoot. 1375 is equal to about, let's say 12,000, okay? So remember, we still have to add this back to this. So our x final is 1375 plus 10,420, which gives us about 12,000 meters. And why do we leave it at 2 sig figs here?
Because in the problem they gave you 2 sig figs.
Yeah, in the problem they gave us 2 sig figs, so we leave our answer as 2 sig figs. So we don't care about all those other things. We round it at the end, and we're good with that. Okay. Any questions about this? So just to review what we did, we took a look at the information they gave us, right? We collected the stuff that was both explicitly said, like accelerates at 50 meters per second squared. That's, you just write down 50 meters per second squared and label as acceleration. We also had some implied information, like starts from rest means velocity equals 0. So we're translating that into math from English. We wrote down all of the things we knew. We wrote down the things we needed to know from the question. We drew a picture, and then we used the equations that we knew from the course to apply to the situation. We picked the ones that were the least work, right? We could have used different equations, like different kinematics equations, and then we'd have to use 2 of them. You don't always. Sometimes you still have to do that, but try to pick the one that makes your life the easiest. And then we went through it. The very important thing is labeling everything, because if you write 3 seconds as like phase 1, then you're going to be plugging in numbers into the wrong thing. So keeping track of all the different variables is why we've got all these 1s and 2s and 3s labeled, okay? That doesn't have to be the notation you use, but just some way to keep track of the different variables is useful.